we want to find the net area between y equal x squared minus 1 and the x-axis from x equals 0 to x equal 2. So I've drawn a picture over here of the graph of y equal x squared minus 1, and you can see here's the interval from 0 to 2. So what we're going to do is divide this up into a number of little subintervals, and then we're going to find little rectangles that approximate that net area between that curve and the x-axis. So the formula looks like this, but it's really pretty simple. This is the width of each of those little rectangles, and this is the height of the rectangle. So to find the length of the little subintervals that we're going to do right here, they're called delta x. That's the width of each rectangle. We just take b minus a over n, which in this case is 2 minus 0 over n, the number of little subintervals we want. So that comes out to be 2 over n. So let's go over here and just take a little look. What if we let n be equal to 4? So we want to divide it up into 4 little subintervals. They would look like this. So 4 little subintervals. Well, delta x then would be 2, the length of the whole interval right there, divided by the number of subintervals we want, which comes out to be 1/2. So now I know that when I do this, I'm going to have a bunch of little rectangles whose width is equal to 1/2. What is the height going to be? Well, for this one, I have to pick one of the values of x in this interval, one in this interval, in this one, and this one. So I'm going to make it easy on myself and just take the right endpoint as the point within that interval. So if I do that, x sub 1 is going to be this number right here in that interval. X sub 2 is going to be this number, x sub 3 this number, and x sub 4 this number. So x sub 1 is going to be 1/2, x sub 2 is going to be 1, x sub 3 is going to be 3/2, and x sub 4 is going to be equal to 2. So how do I go about finding the area of each of those little rectangles? I take this x1 and I find f of x1, so it means I just go down to the curve and over, and I find this area right here. For x sub 2, I go to this point right here and I go to the curve. Well, f of 1 in this case is 0, so that little rectangle has an area of 0. For this endpoint right here at 3/2, I'll go up to the curve and I'll form this rectangle and I'll find its area. And then when I get to x equal 2, I'll go up to the curve and find this area right here. So in each case, the width of the subinterval is 1/2, and then the height of the subinterval is f of that right endpoint. So for the total area under this curve, what I'm going to have is f of 1/2 times 1/2, that's this one right here, plus f of 1 times 1/2, plus f of 3/2 times 1/2, and then plus f of 2 times 1/2. So I can find f of 1/2, that's easy. I just take 1/2 squared minus 1, so I have an actual number for that, times 1/2. I can find f of 1, that's just 1 squared minus 1. Notice that comes out to be 0, and so the height of that rectangle is 0, whether I look at it here or I go to the formula. F of 3/2, 3/2 squared minus 1, I have that number, I multiply times 1/2, so on and so forth. That gives me an area of about 1.75, something like that. Okay, so that's an approximation to the area between this curve right here and the x-axis from x equals 0 to x equal 2. Now let's generalize this a little bit and divide this up into n equal subintervals, and so we know that delta x is going to be b minus a over n, 2 minus 0 over n, 2 over n. So this now is going to be the width of each of the subintervals, and they're all going to have the same width. Now we're going to pick a point out of each one of those subintervals, and to make it easy on ourselves, we're going to use the right-hand endpoint. So for x1, I'm going to have 2 over n, the length of the first subinterval, times just 1. And then for x sub 2, I'm going to have the length of the second subinterval, which is 2 over n, times 2. And x sub 3, 2 over n, times 3. And so for x sub k, I'm going to have 2 over n times k. which is going to be 2k over n. So here's my value of x on the right side of each of those little subintervals. And it's nice because I'm starting at 0 and I'm picking the right-hand endpoint. So it's just the subinterval length times 1, subinterval length times 2, subinterval length times 3, so on and so forth. So now let's look back to our formula right here, and I want to find f of x sub k times delta x. Well, I have everything. Here's x sub k, 2k over n, delta x is 2 over n, so this just becomes 2k over n squared minus 1 times 2 over n. So here I have f of x sub k times delta x. It turns out to be this right here. So I want to take those, add all n of them up, that's what this tells me to do, and then I want to take the number of those subintervals and let it go to infinity. The rest after this is just algebra. This is the thing that we need to get to. We make it easy on ourselves because we're starting at 0 for that original interval right there, and we're taking the right endpoint each time. You could take the endpoint, you could take the value of x sub 1, x sub 2, x sub 3 to be the middle of each of these. You could take it to be the left-hand endpoint, whatever you want. But we're going to make it easy on ourselves so we can get a hold of this formula real quickly. And to do that, we just take the right-hand endpoint each time. Okay, I'm going to erase this and then go to the board, write this down with this formula right here, and then we'll do the algebra. Okay, so the rest is just algebra. Here's my expression right here for the area under this curve from x equals 0 to x equals 2. It's the height of each rectangle times the width of each rectangle. I add all n rectangles, and then I let n go to infinity. So I know that I've got a hold of that area right here. The rest is just going to be algebra. So I look here, 2k over n squared times 2 over n, that's that expression. Minus 1 times 2 over n, that's that expression. Now I know that I can take this summation notation and distribute over this distance, so I'm going to take this sum of this expression minus this sum of this expression. Now when it comes to this summation notation, the variable here is k. The n we can consider to be a constant. So when I take this sum of this expression, I can take the 8 over n cubed outside. What's left is just the sum of k squared. Minus this sum of this expression, the 2 over n is a constant. It comes on the outside, and I just have left the sum of 1. So now I have to use my formula here for the sum from k equal 1 up to n of k squared is this expression right here. There's my 8 over n cubed. And this expression right here, when I take the sum from 1 to n of 1, I just get n. Now I have a little algebra to do right here. So I multiply this out, 2n cubed plus 3n squared plus n. Everything else is the same. Well, 2 over n times n is just 2. I simplify that. Now I'm ready to take the limit. So I want to take the limit as n goes to infinity. I'm not going to worry about the 8 over 6 right here because that's not going to change. I'm just going to have that on the outside. But what is the limit as n goes to infinity of this polynomial over this polynomial? Well, the degree of each one is the same, so that limit is going to be the ratio of their leading coefficients. I don't have to worry about these terms right here as n goes to infinity. So the limit of this over this is going to be 2 over 1. So that's that 2. Okay, minus the limit as n goes to infinity of 2 is just still 2. So I have 8 sixths times 2 minus 2, 16 sixths minus 12 sixths. When I get a common denominator, that ends up to be 4 sixths. The result is 2/3. So finally now I have the area under this curve, y equal x squared, from 0 to 2. The net area, that blue area that I wanted to look for in the first place, just comes out to be 2/3. So look, this algebra right here is complicated. A lot of places to make a mistake. But the idea is, can you follow this all the way down and see that this is really kind of an ingenious method of finding that area under that curve. I divide it up into a bunch of little rectangles, I add all of them up, and I let the number of them go to infinity. What I end up with is the exact net area under that curve. And in this case, that comes out to be 2/3.